to start like a separate call.
Oh wow.
So you have to
but how do I join it?
go to the chat, and it's ongoing call. Do you click on
It
it?
doesn't say ongoing call.
The one with all of us in it, it doesn't say ongoing call.
No.
Are you sure?
I think you just have to click like the little camera button, and it should like. That's what I did.
Show me your screen. Show me your screen.
Hold on. Maybe it's this one. Oh, wait, I'm in it. Wait.
Okay.
All right, can people see my screen?
Yeah.
So everybody can see my screen, is that correct?
Yeah.
Okay, good.
Yeah.
All right, so this was the first part way back when we were talking about thermodynamics, okay? And I'm just going to briefly go through some of these notes and sort of highlight what I'm concerned about. If you want to write this down or, make some kind of notes so you can go back and maybe go over some of the stuff that I talked about so that way you know like what you need to work on. Does that make sense? Okay, so with this test, it's actually a combination of things. You're going to find that it's thermochemistry and thermodynamics, okay? In this section here that I'm going to go over today, the beginning, it's called thermochemistry, okay? And you'll see why. All right, so everybody should know what heat is. Everybody should know what temperature is, okay? So make sure you know the difference between heat and temperature. Really important stuff, okay? The AP exam is really big into making sure you know the difference between heat and temperature. Okay, this graph here, Boltzmann distribution, I would make sure that you understand what it is, okay? Notice that the 1000K party that Justin likes to be part of, okay, that's going to be the rightmost curve. And when you look at it, what's happening to kinetic energy, people? So it's more spread out, right? Okay, so the colder the substance, the more narrow the curve. And notice that you have more particles that are distributed over the curve for a hotter temperature, whereas you don't have it for number of particles. Okay, if I had hydrogen, helium, and argon, okay, which of those three do you think would be part of the 1000K curve?
Argon.
Okay, why?
Because it's the biggest. The mass is the biggest.
But isn't the bigger one slower?
Yeah, it'd be hydrogen because the
Oh, you mean which one's the
faster.
Yeah.
Oh, my
You might want to write that down, Jess. So if it's a smaller molecule, it's easier for it to have higher kinetic energy and therefore it moves faster, right? Okay. Any questions on that slide? We good? Okay. All right. So we're looking at distribution of kinetic energy when we look at the Boltzmann curve. All right. Here's another section that's pretty important. We said, what does the arrow tell us with these particles?
The velocity.
Yeah, right. So the bigger the arrow, what happens to velocity, people?
It increases.
Yeah, so longer the arrow, the higher the velocity, okay? Now notice they show you an example where one side is colder than the other, and as a result, when they come together, they start sharing or transferring their energy in the form of heat, okay? Does anybody have any questions on this slide? Okay, if I don't hear from you, I'm just going to move on. I'll give you a moment to chime in, but if you don't say anything, I'm just going to move on. Okay. I would know the difference between system and surroundings. Okay, remember, system is what is inside this circle or whatever the boundaries are. Surroundings is anything outside of those boundaries. I would know that delta E is equal to Q, which is heat, plus work, okay? Notice that if it's a negative value, that the heat is going outside of the system and into the surroundings, okay? With work, if it's a negative value, the energy is going outside of the system into the surroundings, okay? And I know you can't see that. Well, maybe you can see that at the bottom. It says that work is due to changes in volume of a gas. Can you see that?
No.
Okay, all right. Sorry, it's kind of grayed out with my screen. Okay, so this was just helping us understand like the difference between kinetic energy and potential energy. So the plus delta H symbol means what, people?
I mean, endothermic.
Yay, right. And what did I show you guys that was endothermic the other day?
When you froze like the beaker to the board.
Yeah, right. That reaction is kind of important, okay? I apologize. I did not share the answer key with you. I will share the answer key with you today, okay? Remember when we were calculating delta S and delta H? Do you remember that, people?
Yeah.
Yeah? Okay, all right. Okay, I'm going to skip this. Skip this. Work. Okay. I'm just seeing what else I want to go over with you. Okay, delta H, you should know that it's the heat of the products minus heat of the reactants. Okay, so when you have to do a calculation, you probably have to do something like that with potentially your free response. Okay, so don't be surprised if you see enthalpy of a reaction. Okay, they give you delta H for the first one and then delta H for the second one. And notice that they flip the symbol to represent the endothermic and exothermic reactions. All right. All right, average bond enthalpies. Okay, you'll see something about average bond enthalpies. And remember that when two electrons are further apart, it's high potential energy, but the moment you bring them together, you have low potential energy. And what does that mean? This is really important, guys, okay? I can't star this slide more than I can. Anytime you form a bond, energy is released, okay? Anytime you form a bond, energy is released. Now notice the opposite happens when you're breaking a bond. Okay, with breaking a bond, you have to put in energy. Okay, does anybody have any questions on that?
No.
Okay, all right. I would make sure that you know this equation here. Okay, this is not going to be on your cheat sheet that I give you. Okay, so delta H for bond enthalpy is the summation of bonds broken minus the summation of bonds formed. Okay, you probably will have to do some calculations with this. Okay, so I would go ahead.
Don't we need a chart to get those values?
Yes, yes.
Okay.
So you'll have like a mini chart. Okay, so they'll give you, and they won't tell you which one to use where. You have to figure that out. Okay, so like you'll have a carbon-carbon bond or a carbon-hydrogen bond, or maybe an oxygen-oxygen bond. You know, so you have to figure out what bond numbers to use where. Now, if it's like CH4 and they give you CH bond, what do you want to do? You want to multiply that number by 4. Okay, so you want to keep, I would draw the Lewis structures of any formula that they give you and just count up the number of bonds for that molecule. Does that make sense?
Mm-hmm.
I would do that. Okay, but always remember it's bonds broken minus bonds formed. Okay, does anybody have any questions on that?
After we count up like the bonds broken and bonds formed, would we multiply it by like the stoichiometric coefficient that's in front?
Yeah, so if you have like 2 CH4, you know that there's 4 CH bonds, and if there's a 2 in front of CH4, you would have to double, or you would have to multiply that 4 by 2. That means you have a total of 8.
Got it.
That was a really good question, by the way, Lauren. I like that. Anybody else? Okay, moving on. Yeah, so Zoe, this is the table that I would have to give you.
Okay.
So you just have to pay attention to which one, okay? And this, I believe you guys wrote this down way back when, okay? So like, yeah, sorry, I don't know what I was thinking. Okay, all right. I think this is it. Okay, I'm going to switch to another set of slides, people. Oh, come on. Okay. Here we go. Okay, so this next section here, and by the way, people, I would go back into the hand warmer lab and look at the types of calculations that they made you do for that, okay? Don't be surprised if you see a problem based on that, okay? So make sure you know how to do calorimeter calculations, okay? So obviously I would have to give you 3 out of the 4 to calculate something like this, okay? So you could potentially have to solve for heat or mass or specific heat or one of the temperatures, but I'd have to give you the other 3. Does that make sense? Mm-hmm. Okay.
Wait, is temperature in Kelvin?
Well, see, it's kind of like all over the place. It could be Celsius, it could be Kelvin. I think in your lab it was Celsius. Is that right, people?
No, it's Kelvin.
Did you have to convert it to Kelvin? I'm sorry. Okay, so if they give you Kelvin, you probably want to convert it to Kelvin. But I know I've seen it both ways, so I would just use whatever they give you. Okay. All right. So in this section here, and I don't remember. Did we went over this in class, correct? Does this look familiar, people?
Yeah, we took a picture.
Okay. Just remember that if they're asking you for heat loss by the iron, you are figuring out that based on how much water gains. Does that make sense? They should be equal.
Wait, what should be equal?
Well, okay, you know how you plop something in the water in the coffee cup? You're assuming whatever you plop in the water, if it was hotter than the water, you are assuming that whatever energy it had in the form of heat got transferred to the water. So, Zoe, you're not directly measuring the stuff that you plop directly into the water. You're using the water to tell you how much heat it had. Does that make sense?
Yes.
Yes? Are you okay with that?
Kind of.
Okay, so Zoe, if you had like a piece of metal and you heated it up to a certain temperature and you're trying to figure out how much heat did it actually have inside that piece of metal, what you do is you measure the starting temperature of the water and then the final temperature of the water, which is what they do in letter A here. Do you see that?
Yeah.
So you're not directly measuring the temperature of the metal per se, okay?
Okay.
And you're assuming that whatever that temperature change, you know the specific heat of water and you know the mass of the water. So what you're calculating is the amount of heat that the water took in from that piece of metal.
Okay.
You all right with that? Okay. All right. So this is just showing you if you had to figure out the specific heat of iron, okay? Let's see. Anything else I want to go through? Yeah. They could ask you to calculate the moles based on a chemical equation there. Okay, so notice that if you're given volume and molarity, you could figure out moles from that, okay? And I think you did this in your lab. Correct me if I'm wrong. This is joules per mole. Does that look familiar, people?
Yeah.
Okay, and you were doing heat of solution. It wasn't really a reaction because it was just going from solid to ions. Does that make sense? Are we okay with that?
Yes.
Okay. All right. Let's see. Oh, so notice that for heat of reaction versus delta heat of reaction, whenever you see lowercase q, that's for the calorimeter, but delta H is for the actual overall reaction, okay? Does anybody have any questions about this slide?
So are Q and delta H for the reactions interchangeable?
Let me think about that. I might have to get back to you about that, okay? Possibly. I have to think about that. Okay, Hess's law. I'll tell you right now, there's definitely a problem on the test for Hess's law, okay? So Hess's law, we talked about that way back when, where you just take equations and you flip them or you multiply them by a factor to get an overall equation. Remember how we were talking about like when you drive from one place to another, it doesn't matter how you get there, just as long as you get there. That's what we want to do with Hess's law. So here they're just showing you how they had to rearrange a couple equations to get an overall equation. And are you okay with canceling substances on either side of the arrow, as long as they're on both sides of the arrow?
Yeah.
Are we okay with that, people?
When we subtract,
Uh-huh.
like we won't end up with negatives, like we're just...
No.
Yeah,
because if you look like on the left-hand side for that first equation, it was 3 versus 2. So, Zoe, if there was a 2 on the left and there was a 3 on the right, the oxygen would appear on the right-hand side of the arrow. Does that make sense?
Yeah.
Okay, good. All right. Anybody else with this one? Okay. All right. Okay. Enthalpy of formation. You will definitely have something to deal with enthalpy of formation. And I want to say I made a video for this. Is that correct? Did people watch the video? Okay. All right. Can you guys stop me if this doesn't sound familiar? It should. Heat of formation. Now, this is different than average bond enthalpies, okay? This is essentially how much heat, if you took 1 mole of that compound and you made it from all of its elements, okay? And we know standard state is 25 C or 298 Kelvin. If it's a gas, it's going to be at 1 atmosphere. If it is a liquid, it's going to be 1 molarity, okay? Now, I told you in the video, anytime you have an element in its standard state, its heat of formation is going to be 0, okay? And you should know things like carbon. Okay, carbon, when it's by itself, it's in its element form. Oxygen, when it's a diatomic, that is in its element form. So those substances are going to be 0 for heat of formation, okay? So you want to make sure you pay attention to that. Does anybody have any questions on that one? Okay, so notice that in this chart here, all of the elements, their heat of formation is 0, okay? So you got to remember that if it's a diatomic, one of the lucky 7, that it's going to have a heat of formation of 0, okay? They may not tell you that, so you have to know that. Does that make sense?
But if it's not one of the like elements or diatomics, there'll have to be like a chart or something with the given heat of formation.
Exactly, Lauren. Mm-hmm.
Okay.
Yep. Okay. So you could calculate the delta H of the reactant, and notice there's a degree symbol there, which means it's in standard state, okay? And this kind of looks familiar for some of the other ones that we've been doing. So notice that you use the coefficients when you are using the heat of formation from the table. So you want to pay attention to the balanced chemical equation when you're adding up all these different things, okay? And it's always products minus reactants, okay? This will not be on the cheat sheet, so you need to know this. Any questions about it?
Oh.
Okay, and here's an example where they show you the two substances that are in their elemental form is aluminum and iron, okay? So they're going to have a 0 for their heat of formation. But there should be a heat of formation for the iron 3 oxide and the aluminum oxide, and there is. And the nice thing is there's a 2 in front of aluminum and iron, but there's 0, so it doesn't matter, okay? You just need to subtract your products from your reactants, and they get a negative 854.3. Are we okay with this type of problem?
Yes.
Okay. All right. I'm moving on. So let's see. Oh, someone had a question? Okay. I'm trying to minimize my time here. Okay, so you could have a question like this where they say how much heat is released when 3.56 grams of hydrogen peroxide decomposes into water and oxygen. So the first thing you want to do is convert it into moles, okay? The other thing is you want to pay attention to the coefficients. So notice that there's a coefficient of 2 in front of hydrogen peroxide, okay? So you're going to multiply the moles by the stoichiometric coefficient there, okay? Does anybody have any questions on this one?
No.
We're okay with that one? Okay. Oh, that's it. All right, I'm moving into my last one, so thank you for being so patient. You guys are great, by the way. Oh, shoot. Okay, here we go. All right, last group of slides, people. Okay, so you have to pay attention in this section about what is thermodynamically favored, okay? Trying to see if there's anything I want to say. Okay, I think we talked about this before I left, how exothermic reactions typically are favored, that most of the thermodynamically favored reactions are exothermic, and as a result of it, we get a release of heat, okay? That's all I want to say about that. Endothermic, obviously, it requires energy, but occasionally we can have situations where it is thermodynamically favored, and we'll talk about that in a minute here. Okay. Are we okay with entropy?
Yeah.
So are you guys feeling more confident about entropy?
Yeah.
Okay. Remember, you're looking for the amount of disorder of a system. So if you have a messy room and it gets straightened up, what happens to entropy, people?
Decreases.
Decreases. Good. Okay. So long as you know that. All right. So we know about increasing entropy. Now, say again?
What? I was telling everyone that my room's clean.
Oh. Good for you. So I have not seen like direct questions about like the laws of thermodynamics, but you should have a general idea of the fact that we know energy is conserved, okay? I haven't really seen them say what is the first law of thermodynamics or what is the second law, but I would know the generalized ideas for each. Okay, so I would know that entropy should be constantly increasing. Okay. You should know how does entropy increase. Like they give you some examples here. Obviously, these are all examples where you're going from less disorder to more disorder. So always try to think about that when you're thinking of entropy. Okay. Does anybody have any questions on this slide?
So like, if the question was like, what's this, like, is the entropy increasing or decreasing when there wasn't like an obvious phase change, but it just went from like more moles of like a solid to less? Like, how would we be able to tell with that?
So I would know that if it's going from a solid to a gas, that's the highest amount of entropy increase. Okay. If you're just dealing with gases, that is a big change in entropy. Okay. If they all share the same phase, then I would look at the number of moles.
So which way would it be? Like if it increases moles, does that mean?
Yeah, if they're looking for the greatest increase, I would start looking for the gases. Okay. If the product is a gas and maybe the reactant was a solid. Now you could have like a solid with a gas producing a gas. Okay. And I would say anytime you go from a solid to a gas, that's a pretty high increase in entropy.
But like if it's all gases,
count up the number of moles.
And the more moles there are, that's entropy? Okay.
Yeah. So you would have to say that on the product side there are more moles of a gas to say it increased in entropy.
Okay.
Now they could ask you the opposite, like where is the lowest, or I'm sorry, where is the greatest decrease? Okay, so then you want to look for the least number of moles. Does that make sense?
Yeah.
Okay. I think I have on today's webpage some practice problems. I'm going to put the answers in your inbox. And I think there's some examples of entropy questions there. If there aren't, could somebody contact me and I'll see if I can dig up a couple for you to see? Okay. All right. So this one, it shows you how if you have a solid and it's going to a liquid, you're going from a small entropy to a bigger entropy. Okay. Obviously, when you're going from a liquid to a gas, this is a bigger change in entropy. Okay. So gases always win pretty much with entropy. Okay. I think this is talking about particles. So I don't know who was asking this. Here's a liquid going to more than one gas. Okay, this is significant change in entropy. Okay, so notice that there's a ton of moles of gas, and you're going from a liquid to a gas. So overall, that's a huge increase in entropy. Does anybody have any questions about this one? Okay. So here, this is just an example of a change in entropy too, where you're going from a solid to a liquid. So notice that entropy increases for that one. So I don't know if it was Jess or somebody else talking about when you decrease entropy. When you get condensation or you get freezing, okay, when you're going from a liquid to a solid or a gas to a liquid, okay, you're decreasing entropy. Does anybody have any questions about this one?
Not me.
Okay, all right. You might see this on an AP test, and they're just showing you that obviously going from a liquid to a gas is a huge jump in entropy, okay, as opposed to going from a solid to a liquid, okay? So that's where gases always win, because there's huge jump in entropy, because there's more disorder, there's more random possibilities with liquid to a gas, okay? All right. Oh, our wonderful curve here again, okay? Once again, we have increase in entropy the higher the kinetic energy, okay? Volume increases. Okay, so notice that you have more entropy when you increase volume. So if you have same gas but different volumes, you could talk about increase in entropy. Okay, calculating delta S. So you probably are going to have something like this on the test. Notice that once again, it's just like with delta H. It's standard conditions, and you're looking at the number of moles in front of each substance. So Zoe, you would need a table for this one.
Okay.
Okay. And here they give you an example of it where, and oh, guys, ooh, all right, couple differences here. You might want to write this down. Elements in their natural state, they are not like the delta heat of formation. They have a number, so they are not zero. See how oxygen has a number and it's in its elemental state? It is not zero.
Wait, and what is that?
Okay, with heat of formation, when we're talking about elements at standard state, their number is zero.
Okay.
But with entropy, everything has a number. Nothing is zero. The other difference is people, look at the units. What's the difference between delta S and delta H?
What's positive, what's negative? Oh,
Delta S is in joules.
Uh-huh. And what's delta H in?
Kilojoules.
Kilojoules. Okay, the other thing is delta S has Kelvin in it. Delta H does not. Does everybody see that? It's kind of...
What does delta H have?
Delta H is kilojoules per mole. Okay, so guess what? If you ever have to combine delta H with delta S, you probably need to change one or the other.
Okay.
Okay, and in a minute I'll show you where you want to do that. Okay, now the good news is on your cheat sheet you will have this equation here. Oh, not this one. Where is it? Oh, do I have to go over exothermic or endothermic with you here? This slide here. Are we okay with this slide?
No.
You are not okay with this slide? Lauren, is that you?
I mean, like, yeah, I guess it makes sense, but like we never went over this.
I didn't put this in the video.
No.
Oh, all right. Okay. So in this situation, okay, notice that there's heat going out of the system. So because there's heat going out of the system, the surroundings entropy, okay, is increasing. All right. Whereas the opposite happens with endothermic reactions. Okay. Does that make sense? Because you're increasing the heat in the system as opposed to the surroundings. Sort of like my demonstration the other day, right?
Right.
Are we okay with that? Okay. All right, let's talk about this equation here is on your cheat sheet, and I would use it to your advantage, okay? So Gibbs free energy from the video that I had you show, a thermodynamically favored reaction should be what?
Negative.
Negative, right. Okay. Now, you're going to get really good at trying to figure out, does delta H have to be negative or positive? Does delta S have to be negative or positive? Okay. Temperature is always going to be positive, so we don't care about temperature. But they want to know if enthalpy is negative or positive, what does it do to Gibbs free energy? Okay. If delta S is positive or negative, what does that do to Gibbs free energy? Okay. Now, I would not, where is it? I would not memorize this table unless you really feel like that would help you, okay? The reason why is I always do, by the way, which value is always going to be bigger in number? Is it going to be delta H or delta S?
Delta H.
Delta H, because its units are what?
Kilojoules.
Kilojoules per mole. Okay, whereas delta S is joules per Kelvin times mole. Okay, so it's always going to be a smaller number. Now, notice that when delta H is negative, okay, if delta S is positive, the Gibbs free energy is always going to be negative. That's a given. And that makes sense mathematically. Do you agree?
Can you go get me, Jill? Can you go get me my extension cord and charger, please?
All right. And then the other case, which is not so cut and dry, is the opposite, where delta H is negative and delta S is negative. Okay. Now, because delta S is small, okay, notice that it is thermodynamically favored when T is small. Did everybody hear me?
Yeah, I heard you.
Okay. Now, unfortunately, that is not a guarantee that it's going to be negative, because unfortunately, if T is big, the combination of T times a negative delta S makes the overall Gibbs free energy not negative. Are we okay with that? Yes, no, maybe?
Yeah. Can
Okay.
we talk about what it means exactly when Gibbs free energy is positive?
So when Gibbs free energy is positive, that means that, and you're going to find in the next unit when we talk about electrochemistry, that we are going to have to do work in order to get the reaction to happen. Okay, we might have to add energy to the system in order to make it to work. Okay, so lots of times we're trying to find reactions that go on their own and they do work, but when they're not negative for Gibbs free energy, we have to put work into the system to make them happen. Does that sort of answer your question, Zoe?
Yeah. So if the Gibbs free energy is positive, the reaction can't occur spontaneously, and it needs like an outside force to make it work.
Yes, I like that. Very good. Awesome. Now notice when delta H is positive and delta S is negative, it's not going to be spontaneous. Okay, so it's not going to be thermodynamically favored. And then the last example there is when they're both positive. Okay, when they're both positive, it's only going to work when T times delta S becomes significantly large enough so that the overall number becomes negative. Okay. I would play with these numbers in your head so you can make sure you can tell yourself that. Does that make sense?
Yeah.
All right. Does anybody have any questions on this slide? Because it's kind of important. All right. So no questions?
Wait, would we ever have to figure out like at what temperature?
No.
It would be.
No.
Okay.
No. But you should know that for that last example, if delta H is positive and delta S is positive, that it would have to be an extremely high temperature.
Okay.
Yeah.
That makes sense.
No. So these are more thought experiments than anything.
Okay.
Got it.
Yeah. Okay. All right. Let's see. Oh, so like this, for this example here, guys, you could have a free response like this, okay, where you have to figure out whether or not it's thermodynamically favored, okay? And notice that they give you a way that you would justify it, okay? So you would have to present something like this when they say justify your answer, okay? Does anybody have any questions on this kind of problem? Okay. Okay, this is delta G. This is just like delta H and delta S. Okay. Once again, if you are looking at elements in their standard state, their Gibbs free energy is 0. Okay. Are we okay with that?
Yeah.
Okay. Okay, guys, I'm going to dip my toe in something real quick because I know that you're going to get a question. Yeah, don't you like that? I don't think it's this slide. Yeah, this is, okay, I think it's the last one. I tell you, sometimes we went into equilibrium because we did not address Gibbs free energy yet. So, yes, you have to worry about this when you talk about thermodynamics, okay? And Zoe?
Yep.
So notice that last statement there where they say delta G is the maximum amount of work that can be done by a system, okay? That's kind of why they use delta G. They want to figure out how much work does the reaction do.
Okay.
All right. So I talked about this with you guys in the video, and if you don't remember, you might want to go back and watch it. Notice that if we are talking about equilibrium, delta G is going to be 0. Okay, so I don't know if they're going to ask you a free response that would do this. You know, ask you, you know, what is delta G at equilibrium? Okay, so you would have to tell them it is 0, therefore it does not do any work. Okay, so they could potentially ask you a question like that. I don't know. All right, so in this slide, and I talked about it, they could give you a graph or a chart like this where you see that the reactant on the left-hand side is higher in energy than the product on the right-hand side. Okay, and that's why delta G is negative. And notice going down, oh, I want to go this way. Going down the ski slope, okay, when you hit the bottom of that ski slope, that's where delta G or G is 0, I should say, okay? Does anybody have any questions on this slide? Okay, we're all right with that? All right, and you could have coming from either direction, okay? So they could ask you going from left to right or right to left, depending on what's going on. All right. I kind of think this is an important slide here, so if you want to go back and highlight this, notice that KEQ, when it's greater than 1, by the way, what does that mean? If KEQ is greater than 1, what does that mean?
Products are favored?
Yes, yes. So notice that delta G is negative and KEQ is greater than 1, okay? And have you guys heard of exergonic in physics before?
Yeah, but I don't remember what it is.
Oh, okay. Well, it just means that it's releasing energy.
Oh.
That's all it means. Okay. So this is the opposite where you have a positive delta G that actually is thermodynamically favored. And that's all because either the reactant side or the product side, they end up going down into the lowest point, which is equilibrium. And that's where, I don't know if it was Zoe, this is where you could have a positive delta G and it's thermodynamically favored.
Okay.
But the key is if you have the the reactant, I'm sorry, if you have the product which is higher in energy from the reactant, when you subtract the two, you get a negative delta G. Does that make sense? Are you okay with that?
Wait, I thought if delta G was positive, like the reaction couldn't happen at all.
In this situation, it can't, because see, if you notice that going from the product, which is higher in energy, down to the reactant, that makes it negative. I know it's kind of weird.
So it's starting with products and going to reactants?
Yep.
Oh.
Yep.
Wait, so the C is the products?
D is the product. So you have, if you have pure D, okay, it's not going to stay pure D because it's thermodynamically favored to go into C. Now I'm trying to point in the direction that you're looking at me, but we're starting with D and we're becoming C because that is thermodynamically favored.
Okay.
Are we okay with that?
And so the only way that this reaction would happen is if it was like pure D going to C, or if there was like energy, like giving, constant energy, that it could go from C to D.
Well, actually, if you look, okay, see where there's green on the left-hand side? Do you see how if you had pure C, it would not be okay with pure C either, because pure C is higher in Gibbs free energy than equilibrium. So when you subtract those two numbers, it makes it negative.
Okay.
Are we okay with that?
So it's just trying to get to equilibrium?
Mm-hmm. Yep. Now, if you wanted pure D, you would have to put energy in there because it's fighting you. It wants to go to equilibrium, and you want pure D, okay? So you would probably have to put energy into the system to make it want to be pure D. Are we okay with that?
Yeah.
Okay. All right. Here's an Endergonic reaction where delta G is greater than 0, and notice that it's less than 1, so the reactants are favored, okay? So this is kind of like a Le Chatelier process where you want to shift it to one direction here. So that actually was this one here, I believe. Okay, so see this slide here? They were kind of explaining it with this slide, okay? All right, this one, they're just showing you that at equilibrium, Gibbs free energy should be 0. Okay, so don't worry about that. Okay, all right, this equation, you are only going to get the first one. You are not going to get the second one. Okay.
The second one's just derived from the first
Yeah.
one, right? That's just the same but reversed.
Good for you. I'm so glad you're okay with that. But I know some people start getting a little anxious about it. Okay. You might have a free response question with this. Okay. There's no way you could do a multiple choice because you have the natural log of KEQ. Okay. So you should know. I'm pretty sure they give you the R value. Yeah, I think they do. Okay. Obviously, you should know that temperature is in Kelvin. Okay. And then you're going to look for KEQ. Okay. I haven't seen one where they make you calculate KEQ for this one, but they might give you a reaction where you have to figure out, is this thermodynamically favored? Okay. If you took the natural log of 0, what should you get?
1.
1, okay. And we said that is what? In those graphs, we saw when KEQ is 1, what happens? It's at equilibrium, right? Okay. And delta G should be 0, right? Are we okay with that?
Yeah.
We're okay with that? Okay. So here's the situation where they make an estimate, okay? So they're assuming that standard state is 298, and they know that R is approximately 8. So when you take 8 times 300, you get 2400, okay? So they're saying if delta G is significantly greater than 2400, notice that's joules per mole, that is not kilojoules per mole. Is everybody clear about that? Okay. So they're making an estimation with equilibrium. So if they know that delta G is significantly greater than 2400 joules per mole, then they say that K has to be significantly smaller than 1. Are we okay with that kind of estimation? And then you could have the opposite where they say that delta G is significantly smaller than negative 2400. So as a result of it, equilibrium has to be significantly greater than 1 for KEQ. Are we okay with this slide?
Wait, and when KQ is greater than 1, is it thermodynamically favored?
No, so you're doing the opposite here. You're just trying to estimate equilibrium. You're not trying to estimate delta G.
Okay.
So you know delta G, but you don't know K. So you're trying to figure out what is K if you know delta G. Does that make sense?
Yeah.
All right, anybody else?
Wait, so if K is less than 1, then reactants are favored, and then if K is greater than 1, products are favored?
Yes. So you're trying to estimate KEQ if you know delta G.
Okay.
That's all this slide is telling you. Okay, I think that's it. I mean, this is essentially what I just said. And that's actually what Meredith just said, okay? So you don't have to memorize this table, but you intuitively should be able to interpret the numbers based on what you see, okay? I think that's it. Yep, okay. All right. Does anybody have any generalized questions that they want to ask about what we talked about today?
What kind of questions would be multiple choice questions? Because, you know, like, especially when we were talking about the different equations, you were like, oh, like, this would be a free response.
Okay, so I'm going to go to today. I shared with you. I mean, unfortunately, you're going to have to, you know, be able to do some things, mental math. And by the way, you know what? I actually went on Flynn Prep, and I took their thermodynamics multiple choice. You could do that, Lauren, if you wanted to. And they give you help with it. So if you're lost, they sometimes help you, I think, minimize things. So this is what I shared with you for today. So if you want to look over it, you can. And there's some tips in there.
So will you also be sharing the answers to the problems you assigned with us?
Oh, hold on. Let me do this, and then I'll think about that one. Yeah, I know that's a good question, Zoe. Or is it Jess? I can't tell.
Sorry.
All right. So, Lauren, I'm getting to it here. Oh, here we go. So here are some multiple choice questions. that you can go through. And I like number 5 here on my screen. I like that one because that kind of shows you some of the possibilities of what they can ask you, Here, number 9, you're doing an enthalpy change. Okay, there's heat of formation. So you would have to do mental math for, or you could just write it down and, do the scratch work for it. So does this kind of give you an idea, Lauren, of what possibilities you might have?
Yeah, like it's a lot of concept questions.
Yeah, I'm not saying there won't be mental math. There will be mental math, but there is a lot of concept questions here. I'll tell you right now, this is an older review. So they talk about heat of fusion and vaporization. I haven't seen a whole lot of that, but I've definitely seen like bond energies. I have seen calorimetry, heat of formation. I'm trying to think what else have I seen. Yeah. Okay, does that sort of help you, Lauren?
Yeah.
Okay. So this document, I'm going to give you the answer key in your inbox. Now, going back to the homework problems. So let's see, I got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I had 8 of them. Can you email me your answers just so I can put them in the grade book, and then I will, once you've turned it in, I'll give you a copy of the answers.
When do you want them by?
Well, when do you want the answers? As soon as you give me your answers, I'll give you my answers. How's that?
Right. What about in like the 20.1 to 20.8?
Oh, yeah, that because you've already turned those in, I will just give everybody those answers because that was I think that was Hess's law, right? Or heat of formation or something like that.
Is that the one that was due Friday?
Probably.
No.
Last Friday?
Let's see. I'll go back to last week.
Yeah, we haven't gone over like the last 3 homeworks.
Yeah, there's chapter 6 too that we haven't gone over.
Oh, we haven't gone over that? Okay, let me see. So I didn't do Wednesday. Okay, definitely didn't do.
And then the ones on Wednesday.
Okay, so you need the answers for Wednesday and Friday. Is that right? Wait,
Yeah.
now this is from, I didn't put that in there. Okay, all right. All right, so I got like 3 sets of homeworks I got to share with you.
Yeah.
Okay, all right. I need to talk about electrochemistry with you guys tomorrow. So what time do you guys want to do this? Same time or a little bit different?
Let's do it at 8, like it's real class.
No. Please, no.
Wow, Justin. Yeah. All right. Any suggestions?
Like next week? This isn't the test, right?
No. So sorry, time marches on. I have to talk about new stuff tomorrow. Now, the nice thing is we're only going to do a half hour. We're not going to do an hour. I'm only going to torture you for a half hour.
Okay. As long as so the stuff that we're learning tomorrow isn't going to be on the test Friday, right? No,
but you're going to, how I shared the notes with you there listed under Thursday. You're going to take notes while I talk to you for a half hour.
Got it.
And next week, we're going to make electrochemical valentines. Woohoo! So what time? Tomorrow?
Same time is fine.
1 o'clock? 1 o'clock?
Yeah, same time works.
Okay, all right. Okay, ladies and gentlemen, I'm going to stop recording.